You know, quantum mechanics has this reputation for being, well, just plain weird. And nothing, absolutely nothing, captures that weirdness better than its most famous experiment. For nearly 100 years, a debate between two legends, Einstein and Bohr, has pretty much defined how we think about reality itself. Today we're going to look at a brand new test that finally gives us a verdict. Alright, so here's the game plan. We'll start with light's kind of secret identity, then dive into the classic test that blew that secret wide open. From there, we'll get into the legendary debate it sparked, the incredible new experiment that settles the score, and finally, we'll talk about why any of this still matters 100 years later. So let's get right to the heart of it. Our whole story begins with a paradox. See, at the quantum level, things are not what they seem. Light, especially, has a bit of an identity crisis. This is the question, the one that's been bugging physicists for over a century. And it sounds so simple, right? Is it this or is it that? But the answer? Well, the answer is where things start to get really strange. Just think about it for a second. On one hand, you've got a particle. It's like a tiny little paintball, right? It travels in a straight line. It hits one specific spot. Then, on the other hand, you have a wave. It's like a ripple in a pond. It spreads out. It can interfere with itself. These two things seem completely opposite, so how could light possibly be both at the same time? To try and figure this out, scientists came up with this brilliantly simple experiment, but the result it produced, oh man, it would completely turn science on its head. And this is where we get to this absolutely mind-bending idea called wave-particle duality. It's the core principle that says everything in the universe, from a photon of light to you and me, is somehow both a particle and a wave at the same time. We just don't notice it in our big, clunky world. And believe me, this has been a long journey. It really starts way back in 1801. Then it absolutely explodes in the 1920s with those great debates. And now, here we are, almost exactly a century later, pushing this idea to its absolute limit. Okay, the setup itself is shockingly simple. Picture this. You take a beam of light, you shoot it at a wall that has two little slits cut into it, and on the other side, you just put up a screen to see where the light ends up. That's it. Simple, right? So if light was just a stream of tiny paintballs, you'd expect to see two bright lines on the screen behind the slits. Makes sense, but that is not what we see. Not even close. Instead, you get this series of many bright and dark stripes, and that pattern is a dead giveaway. It's an interference pattern, the classic signature of a wave. This absolutely bizarre result kicked off one of the greatest intellectual showdowns in the entire history of science. It was between two giants, two friends, who just could not agree on what it all really meant. So, Einstein, ever the clever one, thought he had a workaround. He imagined that if a photon went through a slit, the slit itself should rustle just a tiny bit. He figured you could measure that rustle to know which path the photon took, that's its particle side, and still see the wave pattern. But Bohr, his answer was basically, nope, impossible. He argued that the very act of measuring that rustle, of peeking to see which path it took, would destroy the wave. You get to see one identity or the other. You never ever get to see both. So for almost 100 years, that's kind of where things stood. A brilliant theoretical debate. But now, a team at MIT has created the most ridiculously precise version of this experiment ever, stripping it down to its bare quantum essentials. And the technology they're using is just wow. Instead of actual slits cut in metal, they're using individual atoms, over 10,000 of them, super cooled to just a fraction of a degree above absolute zero. They use lasers to hold them in place and even tune their fuzziness. And then they just sit back and watch single photons scatter off them. I mean, this is the experiment in its purest possible form. As the team leader, Wolfgang Ketterle, put it, what they did was an idealized Gedanken experiment. That's a fancy German word for a thought experiment. They basically took this argument that Einstein and Bohr could only have on a blackboard and they built it for real. So, the moment of truth. After a century of arguing, of wondering, what did they find? Who was right? Was it Einstein or was it Bohr? The whole thing really came down to this one question. Was Einstein's idea of a physical rustle, some sort of mechanical kick to the slit, the real reason the wave pattern vanished? And the answer from the experiment was a single definitive word. No, that physical kick, that little spring in the slit, turns out it wasn't the important part at all. What really matters is something much, much weirder. It's all about information. See, the modern view which this experiment just nailed down is that if any information whatsoever exists anywhere in the universe about which path that photon took, what they call which way information, the wave pattern just goes poof. It's about what is known, not about physical force. So yeah, the verdict is in. Bohr was right. The team proved that the more which-way information the atoms had, the weaker the wave pattern got, and this happened even without any physical springs or rustles. The real secret sauce here is something called quantum entanglement, the spooky, invisible link between the photon and the atom it bounced off of. Okay, so a century-old physics debate is settled? Cool. But why does this matter to us right now? It's actually much bigger than just a historical curiosity. Well, for one, the timing is just incredible. This result is coming out almost exactly 100 years after quantum mechanics was first written down. It just goes to show you that even after a full century, we are still digging up these profound truths hidden inside the theory's foundations. So if there's one big mind-bending idea to take away from all this, it's this. At the quantum level, looking at something isn't passive. The simple act of gaining information about what's happening fundamentally changes what happens. And that, of course, leaves us with the ultimate head-scratcher. If reality is different when we measure it, what is it when we're not looking? That's the deep mystery at the very heart of the double-slit experiment. And honestly, it's just as baffling and just as awesome today as it was 100 years ago.